Everyone. Today we are going to look at the design of AC coupled resistive feedback inverter. So in this video, we are going to cover the basic understanding of the circuit. Then we'll talk about the DC analysis, AC analysis, and eventually we'll talk about the design and simulation of the circuit. So, all right, let's start. So let's break this circuit into small pieces first for clear understanding. So this is one part of the circuit, inverter. Okay. So we have this V in over here, then V out over here, right? So what is the gain of the circuit? Gm of n plus Gm of p over GDS of n plus GDS of it minus. So it's nothing but Gm of Gm equivalent times R equivalent. That is what I have written over here. So this is N type device and this is P type device. Okay. Now, if we plot the curve input and output, which kind of relation do we expect? Let me show you. So this is a kind of a we will get. The x-axis we have V input, on the y-axis we have V out. And if we draw a line like this, where V input equal to V output, we'll find that this is the optimal biasing point. What do we mean by optimal biasing point? Which means that the gain in this stage is maximum. If we just take the V out, dV out over dV in, then we'll find out that the slope is maximum over here, right? So we need, if we want the high gain from this circuit, we need to make sure that V input equal to V output. Okay. So we have understood that if we want the maximum gain from this inverter, we have to bias this such that the V out equal to V input. How can we do that? So we can understand it in this way, that both P-type device as well as the N-type device is connected in the diode connected manner, right? So what will happen if I assume that both have the same strength, right? Then this V out will be settled at VDD by 2. That will be its trip point. Right? Now the problem with this structure is that we cannot apply input, right? So how can we isolate the V output and V input? So there is this structure called drain feedback biasing for the MOS. So what is it exactly? So let's say this is I bias for my NMOS, right? And here this is V input. So this is a resistive feedback biasing, right? So instead of shorting the V input and the V output directly, right? We have connected these two terminals through a resistance, right? So we have isolated the V input and V output, although there is no current flowing from drain to gate, right? So similarly, the same thing we can do over here as well. We have this inverter, right? Then we can connect one resistance feedback, and here we have the input. This is up here, right? So another way of looking at this circuit is assume that this inverter is going to work as an amplifier, right? So how that amplifier looks like, let's say this is minus A, gain or let's say gain of the amplifier. We have, this is V input, this is V output, and we have a resistance connected between input and output like this, right? So this is one more way to understand that it's feedback with a resistance RF. So this circuit is called self-biased. Let's say there is no input, right? And we are just taking the output. Then it is called the self-biased resistive feedback inverter. Okay. All right. Now, what if we have an AC signal whose input common level we want to reject? This is AC signal, right? It's common mode level we know. Right? This is a common mode level. If we want to reject that common mode level, right, and amplify this circuit at the same time. We need amplification. Okay. And what we can do? So this is the coupling capacitance. We have one input, right? So this is the coupling cap. So what it will do? It will reject the DC, right? So it will reject the common level. Now we can use our circuit over here. This is the resistive feedback. Here, let's say we have one load connector. So what this circuit will do now? Right? So first of all, the DC common level will be rejected. Then we know that this whole circuit is working as an amplifier. Right? So this is going to amplify the V input by some factor. Let's say this is my V input and it has the DC common level of 0, DC level of 0, and its amplitude is 100 millivolt to minus 100 millivolt, so which is 200 millivolt peak to peak. If what do I want? I want the amplification as well as the DC level, right? So its DC level is at 0. I assume that the DC level for my output will be somewhere here because this self-biased inverter is biased at the trip point, right? Which is almost equal to VDD by 2, close to VDD by 2, let's say, right? So this is VDD by 2. So how my output will look like? This is my input plus 100 millivolt to minus 100 millivolt. Right? So I'm not going to plot it in a perfect, scale version. We just get the basic understanding. I mean, how the amplification, how the output should look like. Take the peak over here, then come down, then cross it, then take the peak over here, then come down, and again, something like this. This is the kind of output you should expect where we have rejected the DC level. Now the new common mode level of the circuit is this one, VDD by 2, and output is also amplified. The condition is for this amplification, we have seen that we have this A naught gain of the amplifier, and we have this resistive feedback connected to the input and output, right? So if I just talk about the inverter, then my gain is Gm of n plus Gm of p times RO1 parallel RO2, or Gm equivalent times 1 over Gm equivalent. That is Gmn plus Gmp over GDS1 plus, GDS of n plus GDS of p. Right? So this is also n and p. So we need to make sure that this whole quantity Gm times R, or Gm over GDS, should be greater than or equal to 1. Right? So that is the criteria for the amplifier. Otherwise, the input signal will die down. Right? So if we draw the equivalent small signal model of the circuit, we'll find out that in order to keep the gain greater than 1, we need to make sure that this RF, right, is greater than RO L parallel ROT. So that we need to make sure, so that this structure, this self-biased inverter structure, can work as amplifier. So that was all about the basic understanding of the circuit. Now the interesting part, let's jump directly onto that: implementation and the simulations.
Okay, so this is the circuit we were talking about. We have inverter formed by PMOS and NMOS. Then we have resistance working as a feedback, one AC coupling capacitance, and one load for the simulations. Okay, let's go to the rest bench which I have already created. So for now, I'm taking some initial values for the elements available in the circuit. So the value of RF is 100K, V peak to peak is 200 millivolt, input frequency of the input signal is 20 megahertz, and the supply is 1.2 volt. Okay, First, let's try to run the DC simulation. So we can see that the V out is close to VDD by 2. It's not exactly a VDD by 2. Why it's happening? Okay, let's check that. The size for PMOS is 1 micro, and for NMOS is also 1 micro. Okay, so the strength for PMOS and NMOS is not same, right? So NMOS has higher strength, so it is going to pull the V out to ground side. That's why the V output is not close to VDD by 2. So what we can do, we can increase the PMOS size so that it will try to pull the V output towards VDD by 2 or VDD. Let's try to change the multiplier to 2. Let's see what will happen. Run the simulation again. So now we can see that V output is more close to VDD by 2. It has improved by almost 30 millivolt, right? So this way, if we can create the same strength for PMOS and NMOS, this will be almost, the V output will almost be at VDD by 2. Okay. So from the DC analysis, we can see that this input node of the inverter is close to VDD by 2, right? Now let's try to run the remaining simulations, transient and AC. I have already done the simulations for you. Let's see what we can understand from those waveforms. Okay. Okay. So this one is the waveform for transient analysis, right? So this is the V input, and this one is the V output. So what we were expecting from the capacitor is that to reject the DC, right? So input was having the DC of 0. As we can see, the input of inverter, right? The output of the capacitor. The output node of the capacitor is having the DC of close to VDD by 2, right? So that was the motive of capacitor. So it's working fine. So this V output is the amplified version of the VA, right? So the whole circuit is working fine. Let's have a look at the AC analysis, the AC analysis waveform. On this waveform, we can say that the circuit is behaving as a high pass filter. Okay, so we are going to cover the AC analysis in detail in the next video, where we are going to discuss how this circuit is going to behave as the band pass filter. Okay, so we have to be very careful to make sure that the input frequency is falling within the band of that band pass signal. Otherwise, it will not be amplified as per our expectations. Okay, so that was all for this video. Thank you.